Hello, everybody. Welcome to my channel. Welcome to rocketry. I thought I would make a little series on rocketry, also known as the art of controlling explosions. It's a really interesting topic. I myself am a mechanical engineer, mainly working in the propulsion space, and I hope this is a good little introduction. I'm going to start by covering a lot of breadth, and then I'm going to try to move into depth of propulsion physics, systems, perhaps orbital and flight mechanics, things like that. So if you find that interesting, just give this a watch. Let me know what you think. YouTube has really been filled with an influx of AI content, AI scripts, and just AI voices. So I thought I would go ahead and try to make a video that actually has a little bit of effort and a topic that I'm passionate about. So I'm going to start from a basic Newtonian perspective. Newton's laws of 1687. You've probably heard of Newton's three laws. Newton's first law, being the law of inertia, is essentially that an object at rest is going to stay at rest, and an object in motion is going to stay in motion until a force acts upon it. So all this means is that if you are a rocket in the vacuum of space and you have some velocity, there's no frictional forces in space, so you are going to remain at a constant velocity until you are acted upon. Moving to Newton's second law, the very famous equation, force is equal to mass times acceleration. And we have a little diagram here that I drew, yours truly, where you have a rocket with some mass and your propellant is being expelled, creating a force. You're reacting against that force, creating an upward acceleration. So there's F equals ma in action. And Newton's third law, arguably the most important, though they're all pretty important, so perhaps not, but very important to rocketry is the idea for every action there's an equal and opposite reaction. So if your propellant, if your exhaust is creating some sort of downward force, which we can define as an action, you're going to have an upward reaction, and that's essentially the basis of all rocketry. You are reacting against the expulsion of mass at a velocity underneath you. So there's Newton's first three laws. Embed these into your memory, incredibly important. Next up, I'm just going to make a basic distinction between mass and weight. So mass is something that's intrinsic to matter. It's independent of a gravitational field, and the general unit for that is going to be kilogram. I'm not really going to cover any units in the imperial system. I like to keep things all metric because, why make rocket science more torturous than it needs to be with slugs, pound m, pound force. It just seems a little unnecessary. So that is your mass, defined as a kilogram. And then you have a weight, which is a force. So again, going back to our equation, F equals ma, Newton's second law. So it's the force of gravitation on mass. So this is dependent on a gravitational field. And all gravity is an acceleration, essentially. And acceleration, of course, is a change in velocity. Velocity is a change in position. So plugging in, we can define weight as our force W is equal to our mass times G. G being a gravitational constant of a body. Generally, this is going to be Earth. Earth's is 9.81 meters per second squared. If you don't know where this comes from your gravitational parameter times a mass over the inverse of your distance squared. So very famous equation here. So your weight is going to, and the general unit for this, or for any force of that matter, is going to be a Newton. So your weight is dependent on a gravitational field. So that's why they say you will weigh differently on the moon. Your weight will be different in vacuum, on Venus, on any other body, going to be dependent on the gravitational field that you're in, while your mass is intrinsic and will be the same just about everywhere in the universe. Moving on to the conservation of momentum. Conservation in general is incredibly important to physics. This is generally derived from symmetries, and all symmetries is essentially ensuring that physics are the same everywhere in the universe. You have space-time symmetries, you also have some gauge symmetries, though that's a whole other topic. But essentially, as far as momentum goes, the universe has certain constraints, and physics likes to do a lot of bookkeeping, a lot of accounting, to make sure that you don't have energy created out of nothing or weird things happening. So if we have a little diagram down here showing how momentum specifically is conserved. Let's say you're in a vacuum, and again, the general equation for momentum is P equals mv. So P represents your momentum, and all that is a mass times velocity. Also notice how a force is a mass times acceleration, while momentum is a mass times velocity. Momentum is also a vector, and so all a vector is just something with magnitude and direction, unlike a scalar term. So all that means is rather than just running 5 meters per second, you're running 5 meters per second in some direction, like east. So here we have a little example. Let's say you weigh 100 kilograms and you throw a ball that weighs 1 kilogram. If you were to throw this ball at 10 meters per second to the right, you would have a leftward velocity because you were conserving momentum with the ball you're throwing. And if you take your mass times velocity for each side, both sides are conserved, your momentum is conserved. Going back to Newton's third law, for every action, there's an equal and opposite reaction. The same exact idea can be applied to rockets. The only difference with rockets is what you're doing is instead of throwing a ball, you were throwing billions of tiny balls, well, gas molecules, of your exhaust every single second. So just like you throw the ball to the right and you gain velocity to the left, the rocket is expelling mass very quickly down, which if we define our downward direction as negative, upward is positive, your negative momentum summed with your positive momentum is going to be zero since momentum is conserved in the system. So that is essentially the basis of rocketry. You're basically manufacturing backwards momentum for the rocket to react against. That's why it works in space. You see, the way that planes work, the way that cars work, cars react against the ground through the force of static friction. Planes react against the fluid of air, creating lift. But you don't really have anything in the vacuum of space to react against, so you have to bring your own. You have to bring your own things to expel to react against. And the case in chemical propellants is through chemical reactions where we can expel tiny molecules very, very quickly outward to create large momentums. Moving from there to thrust, all thrust is a force that's produced by a rocket engine in a given instant. So you're basically creating force by ejecting momentum per second. So force is going to equal m dot times velocity, your thrust force. M dot is simply a mass flow rate, and V in this case is going to be V subscript E, which is just the velocity of your exhaust. And it's a mass flow rate, and the unit for that is kilograms per second. This can be imagined because your rocket is essentially throwing mass out every single second, so you have a mass flow. And going back to this, force is just the time rate change of momentum. As you can see, F equals m dot V, P equals mv, so F is equal to dP over dt. And moving from there into impulse. Impulse is essentially just the total push your rocket engine delivers over a given amount of time. So if you have thrust, which is essentially the force generated by your rocket engine over time, all it is the area under your thrust curve. So impulse is just the change in momentum of the rocket, also known as delta P. And this is represented with a capital I, also the integral of F, the integral of your force. So the units for this being F times T is just Newton seconds. This is used to classify rocket motors and just generally very important in rocketry. Now I'm going to cover why getting to space is so hard. Earth is obviously a very large object, so we are confined to a sort of gravitational well that is incredibly difficult to climb out of. And velocity in many ways can be viewed like currency. It's very expensive to attain. And there's also many forces that create sort of downward losses on our rockets. So the whole point of a rocket is to get a lot of upward acceleration, upward velocity to escape the gravitational potential of Earth. And that can be a very difficult thing, primarily due to three factors, though there are also other factors that go into this. The largest one is gravity drag. Existing in a gravitational well, if we take the idea of gravitational curvature, imagine sitting a heavy ball on a trampoline. You're going to have this very deep well that you need to climb out of. And, if you've ever fallen down a well, it is pretty damn hard to climb out of. And this is derived from Newton's law of universal gravitation. Very important, where basically every mass attracts every other mass with a force proportional to the product of masses and inversely proportional to the square of distances. You've probably heard of the inverse square law. It comes up in many places in three-dimensional physics. Though essentially, as we said, gravity acts as an acceleration. So if you have some mass applying an acceleration, you have a downward force, or to the center radially of Earth's body. So if you're trying to go upward, you have a massive amount of drag caused by gravity. Then you also have atmospheric drag or aerodynamic drag. So another good term to define is simply pressure, which is just a force per unit area. So if you have a force over an area, the unit for that would be Newton over meters squared, which is also the definition of a Pascal, which you've quite possibly heard of. The pressure of the atmosphere creates kind of frictional forces that oppose motion as you move through a fluid. If you can think about swimming, it has a much greater density than air. So you're going to have a large drag force as you swim through water compared to, say, running through air. That being said, though, here's the equation for drag, which is d equals 1/2 rho c sub d a v squared. So c is essentially your drag coefficient, which you've probably heard of. Rho is the density of a fluid. The unit for that is generally kilograms over meters cubed. So you can imagine some mass amount of your fluid taking up a volume. And then your area is your cross-sectional area, which is the whole reason that a parachute works. It's the whole reason we create rockets very tall and skinny, because if they're not, then their aerodynamic forces will create a lot of inefficiency and structural problems. And then just take note of this v squared term being exponential. As you increase velocity, your drag force increases considerably. And that creates a lot of problems. And then you also have steering losses presented by the rocket. If we take this diagram here, ideally your thrust angle is going to be perfectly vertical, but in reality that never happens. That can be due to various reasons, some good. Though you kind of have a cosine loss, just your force equal to force times cosine of theta, where theta represents your thrust misalignment angle, or the angle between your thrust vector and your velocity vector of the rocket. As you can see, it basically creates a horizontal component, which isn't fantastic for maximizing upward velocity. Next up, I'm going to cover thrust to weight ratio, TWR. So this is just the total thrust of your rocket engine to the total weight of it, T over mg. Remember, W equals mg. Typical values for large rockets are around 1.2 to 1.5. There are kind of trade-offs to thrust to weight ratios. You do want a decently high thrust to weight ratio for greater acceleration, but as you do that, remember the v squared term in your aerodynamic drag equation. You're going to create a lot more Q, is essentially the representation of that. If you've ever watched a rocket launch, you've probably heard them reach max Q, which is somewhat of a commonality, and that's basically when aerodynamic stresses are at their maximum, and this is what you design many structural frameworks of a rocket for. So it's essentially a balance between wanting a lot of acceleration, a lot of delta V, but also mitigating your maximum aerodynamic stresses. And upper stages of rocket have a much lower thrust rate ratio because you have no weight to overcome in a vacuum. The main kind of idea of thrust-weight ratio is that your thrust exceeds your weight, because if it doesn't, if your weight, which is a downward, if your weight, which is a downward acting force, exceeds your thrust, which is your upward acting force in a rocket, you are probably not going to have a great time leaving the ground. And finally, I'm just going to cover the famous Tsiolkovsky rocket equation. This is arguably one of, if not the most important equations of rocketry. It's essentially applying Newton's laws to a variable mass system, where you have something like F equals ma is kind of defined for a constant mass. In a rocket, obviously you are expelling a lot of mass through your propellant reactions. And the question becomes, how do you calculate, say, a change in velocity? How do you calculate a change in velocity when you have a variable mass system? And that's kind of why we use conservation of momentum. So if we take your rocket's momentum at one instant in time, defined as t, all we can say is that p is equal to mass times velocity, or momentum is equal to mass times velocity. Now take a small amount of time, we'll represent with dt later, we'll call this t plus dt. In that time, the rocket is going to eject a dm, a small amount, a small change in mass. So this term becomes m minus dm. And then you're going to have a new change in velocity upward, so you're going to have v plus dv. But then you also have to take into consideration your expelled mass dm, and the exhaust speed relative to your rocket. So that's going to come v minus ve, where v sub e represents the exhaust velocity. So your momentum before at time t is going to be mv. Your momentum after is going to be m minus dm times v plus dv plus dm times v minus v. So in blue here, I represent your rocket momentum, and this is the momentum from your exhaust. So all we have to do for conservation of momentum is set your momentum before to momentum after. And from there, you can cancel many terms. You can subtract this mv to the other side, and the minus vdm and the plus vdm term cancel out here. From there, you get 0 on this side, which is equal to mdv minus dmdv minus v sub e dm. Now, dmdv is a second order term. It's incredibly tiny, so you can generally neglect that in most mathematical domains. So that is going to approximate to 0, leaving us simply with mdv minus ve dm. From here, we can divide out an m on both sides, leaving us with dv is equal to negative ve dm over m. Again, since the whole point here is trying to find the change in velocity in a variable mass system, we want to isolate this to one side. And from there, all we have to do is integrate the dv, since we're after a velocity here, and we're going to integrate that from our initial velocity to our final velocity. Again, setting that equal, and then we're going to integrate our dm over m term from our initial mass to our final mass. Now note here, our initial mass is often called our wet mass, so that is basically your off-the-ground mass when your rocket is full of its propellant. And your final mass is often called the dry mass after burnout, when all of your propellant has been burned. So all that becomes just Vf minus V naught. Or in this case, it would be subscripts, of course. So V sub F minus V sub 0 is going to be equal to your exhaust velocity. And dm over m, from your calculus days, you'll remember is simply an ln. So that becomes ln of your mass final minus ln of your mass initial. And if you remember the way logarithm works, when you subtract them, you can then divide them, getting our final Tsiolkovsky rocket equation derivation here, where you have delta V, since final minus initial is just going to be your change in velocity, is equal to your exhaust velocity times the natural log of your initial mass over dry mass. So it's essentially momentum conservation integrated over a continuous mass loss system. And the logarithm creates a lot of kind of punishing realities for rocketry in strong gravitational wells, because essentially what you're trying to do is accelerate while also making yourself worse at accelerating, because each unit of delta V that you would like to add requires more fuel, which is going to increase your initial mass, which makes that fuel less effective. So you get diminishing returns essentially once you get to a certain size of rocket. So that's about all I have for today's video. Getting to the Tsiolkovsky rocket equation, some basic kind of elements of rocketry in general. So if you found this interesting, if you found it informational, let me know if there's anything that could be worked on. Hopefully it was somewhat informative. Moving on from this, I would like to make a video about propulsion physics and engine theory. I would like to get into rocket propulsion thermochemistry,